So in the last two previous videos we had discussed about how to calculate the head loss due to friction, which is a major loss. Then I have solved one of the example, or I have solved one of the equations to solve for minor losses. The minor losses that I solved is sudden enlargement. I hope you all remember that I had solved this equation called head loss due to sudden enlargement, which can be given by v1 minus v2 whole square divided by 2g, where v1 is the velocity at the first point and v2 is the velocity at the other point. Okay, so we had solved this, and with respect to the derivation that I have solved, similarly the derivations for others also exist, but we are not going to solve all of that. For your syllabus, we need to solve the derivation for only friction loss and then the sudden enlargement. But I'll give you all the equations from which you could be able to calculate the head loss. So the head loss due to entrance can be calculated from this equation, which is 0.5 v square by 2g, and the head loss due to exit can be calculated by v square by 2g. V responds to the velocity that is corresponding to the entrance and exit. Like for example, if I have to calculate how much is the head loss due to entrance, I need to calculate how much is the velocity immediately after the entrance. Similarly, if I had to calculate how much is the exit loss, I must calculate how much is the velocity before the water exits from the pipe. What is the velocity here? Okay, so if I know what is the velocities at both the points, I could be able to calculate how much is entrance head loss and exit head loss. Now similarly, we know what is sudden enlargement, sudden contraction, and all those equations. This is the loss due to pipe fittings. Okay, so once we have understood all the losses that will take place when the water travels from one point to another point, so we have understood that there is a loss of energy that takes place when water travels from one point to other point. The next step is to try to interpret those losses and use them in understanding the fluid flow problems, right? So let us take an example. I'm going to take this example where there are two tanks. This is your tank 1 and this is your tank 2. Tank 1 and tank 2 are connected by a pipe which is having a length of L and diameter D. So in these two tanks, it is connected by a pipe. Now what we need to understand is when water travels from tank 1 to tank 2, you would like to see how much is energy that is lost. We need to calculate how much is the energy that is lost. Okay, so first what we'll do is we'll try to understand this figure. So in this figure, these are the two tanks, and this is the level of water in the tank 1 and this is the level of water in the tank 2, and it is connected by the pipe which is completely horizontal. As you can see, this is some datum that I have considered. So this datum, with respect to this datum, this is your elevation. The center of the pipe is at an elevation of Z1 and this is at Z2, where if this is horizontal pipe, Z1 will be equal to Z2. So here the elevations are remaining same for the entire pipe. So this is not an inclined pipe in the upward or in the downward direction. Okay, so we have understood this setup. So first what we'll start doing is to try and interpret what could be the loss that will take place. Okay, so if I tell you what is the energy at any given point, what you can do is that you should be able to calculate the total energy by taking the sum of three different energies. So what are the three different energies that we consider? One is pressure head, the next is velocity head, then we will take the datum head, right? So this is what our total energy at any given point. Now if I tell you to calculate how much is the total energy in this tank, so what you do is that you take the pressure energy, kinetic energy and datum energy. Now you tell me what will be the velocity inside the tank. Inside the tank there is no velocity, the water is not flowing, it is in static condition. So the velocity will be, head will be equal to 0. So what is left over is the pressure head and the datum head. So as we know, this is what our datum head is. Now this is our pressure head. So we all know the equation. So P is equals to W into H. Right, so what is pressure head is? Pressure head is given by P by W, right? So which is head. So H1 is representing the pressure head at the tank 1. Okay, so which is P1 by W. Okay, so once we understood what is the total energy at the tank 1, similarly we can try to identify how much is the total energy at the tank 2, which is P2 by W plus of Z2. So we understood what is total energy at these two tanks. Now when we know what is total energy, so the difference of total energy in the tank 1 and tank 2 will give you how much is the energy that is lost. Okay, so this is one way of interpreting how much is the energy that will be lost. So this is your total energy. What is the total energy here? P1 by W plus of Z1. This is your total energy. Now here the total energy at the tank 2 is P2 by W plus of Z2. So this total energy minus of this energy will give you how much is the head that is lost. Okay, now there are two reasons that the energy might be lost. One is the major loss, the other one is a minor loss. So in the major loss, it will be because of the friction that is exerted on the flowing water by the pipe material, and then we know that there are other two minor losses that will be encountered in this case when the water enters into the pipe and when the water exits into the from the pipe, right? So these are the losses that will take place. Now what I will do is I will make a graphical representation of the loss of energy at various points. Okay, so first what we will do is let me assume that this is the total energy that we have. This is from here to here, this is the total energy that we have. Now as we know, this datum is going to remain constant, so I am going to neglect these datums. Okay, I will consider from the center of the pipe till the free surface of water in the tank 1. So this is your total energy that we have, and as I told you, when water enters into the pipe, there will be energy that will be lost, and this energy that is lost we will call it as loss of energy due to entrance. And how much will be this energy loss? It will be equal to 0.5 V square by 2G. Now see, there is a sudden dip in the line. Okay, this sudden dip is because of entrance loss. The energy is lost due to entrance. Now as we know, this is linearly reducing energy loss. And what is this linearly reducing energy loss is representing? This blue line. You don't focus on the red line, red dotted line that I have represented, this blue line. Okay, so what is this representing? This is representing how the energy is lost linearly with respect to the friction that is exerted on the flowing water. Okay, so this frictional resistance is reducing the energy gradually. Okay, so that is why this is gradually reducing energy. So once it reaches this point, now this is the energy before the exit. Before the exit, this is the energy that we have. After the water, when it enters into the tank, because of the loss of energy due to exit, there is again sudden dip is there. This sudden dip is due to the loss of energy due to exit. So how much is this? This is V square by 2. This is a V square by 2G, which is exit loss. This is your entrance loss. So I'll call this as entrance loss. This is our H due to exit. Okay, now if I take how much is the difference between this, if I take a horizontal and then I try to define how much is this vertical, so this vertical is going to represent head loss due to friction. So you already know what is the head loss due to friction equation, which is FL V square by 2GD, right? So the Darcy-Weisbach equation, which we had derived in the previous class, is the equation to calculate how much is the head loss due to friction, right? So I have accommodated the head loss due to entrance, head loss due to friction, head loss due to exit. The sum of these three will be equal to what is the difference of total energies in tank 1 and tank 2. Okay, so we already know how much is the difference of energies between tank 1 and tank 2. How much is this energy? This is H1 plus Z1, this is H2 plus Z2, where Z1 is same, will get cancelled out. So the difference of H1 and H2, H1 and H2 is how much? This is H. So what is H is representing basically, if you try to understand? So H is nothing but the difference of water level in two tanks. If I calculate how much is the difference of water level between the two tanks, it will give me how much is H. Now what is this H equal to? H is equal to sum of all the losses that is going to take place, right? So this is how we will try to interpret the energy that is changing, the energy that is getting reduced in the flow of water. Now once we understood, the line that I have drawn here, will be called as total energy line. Okay, so it is a graphical representation of change of total energy with respect to the flow of water. If you try to determine anywhere, if for example if I take a section over here, at this point I want to understand in the pipe how much is the energy that the water has got. I can calculate by taking the vertical of this. So I will measure how much is this vertical, whatever the plot that I have drawn, I will determine how much is the energy that is available. So at every given section, at every given point, we can determine how much is the total energy by drawing this line. Okay, so once you have drawn the total energy line, the next step is to determine what is your hydraulic gradient line. Okay, so in hydraulic gradient line, what we do is that we consider only pressure head. We will not be considering velocity head. So I told you there are three energies, right? So pressure head is there, velocity head is there, then we have datum head. Now what I will do is, if I neglect what is velocity head, if I neglect velocity head and I only consider what is pressure head, okay, so this is called as piezometric head. You already have studied what is piezometer. So piezometers are those instruments, they are very simple instrument to measure the pressure head at any given point, or if you can calculate the pressure at any given point. Now what I can do is that if this is a pipe which is flowing with water, if I insert a tube here, a glass tube, if I insert a glass tube here, whatever the level of water that will be raised in the piezometer, whatever the level of water that will be raised in the piezometer is called as piezometric head. Okay, similarly at any given point we can place a piezometer and we can see how much is the height of water that will be raised in the piezometer. That will be representing how much is my piezometric head. Now if you try to imagine, similarly if I have to place the piezometer at every point along the length of the pipe, whatever the water level that is raised in the piezometers, if they are connected by a line, it will be called as hydraulic gradient line. Now if you can see in this figure, this is the piezometer that I have installed at this section, and this is another piezometer which I installed at this section, and the water levels as you can see that has raised in the pipe, if they are connected by a line, so that line I am going to call it as hydraulic gradient line. And hydraulic gradient line is basically the sum of pressure head and datum head. Okay, so what is hydraulic head? Hydraulic head is basically the summation of pressure head and datum head. And what is total energy? Total energy is the sum of pressure head, velocity head and datum head. Okay, so if a line that is drawn with respect to the total energy at every given section, it will be called as total energy line. And if I draw a line which is representing the piezometric head, it will be called as hydraulic gradient line. Okay, so this is what we need to understand about the hydraulic gradient line and total energy line. So once we have understood all of this, what we will do is we will make a simple interpretation of this entire diagram by some equations. Okay, so what we will do is, as I explained earlier, total energy at tank T1 is equated to total energy at tank T2 plus of head loss. Okay, so as we know, P1 by W plus of Z1 is equals to P2 by W plus of Z2. Z1 is equal to Z2, so that is why it is getting cancelled. So P1 by W minus P2 by W is equal to HL. So I can say that P1 minus P2 by W is equals to HL. So we know that H1 minus H2, what is H1? This head and this head, which is basically P1 minus P2 by W itself. So H1 minus H2 is equals to small h. Small h is representing difference of water level between the two tanks. So small h is nothing but your HL. What is your HL? HL is the head loss. Now going to HL, so if I tell you to interpret what will be the HL, it will be equals to the sum of all the losses that has taken place. The first loss that you need to consider is the loss due to entrance. Then we need to consider the head loss due to friction. Then we are considering the head loss due to exit. Okay, so this will be either equal to the total the difference of water level between the two tanks, or it is equal to total head loss. Okay, now what I can do is that I can neglect these minor losses, because anyhow they are minor in nature, they are not major in nature. So we will consider only major loss, we will neglect the minor losses. If neglecting minor losses, what will be the capital H equal to? Capital H will be equals to head loss due to friction itself. So head loss due to friction equation is FL V square by 2GD, and we already know what is the continuity equation. Q is equals to A into V. So V will be equal to Q by A, or else V square will be equal to Q square divided by A square. So this is a pipe of circular section. So area will be equal to pi by 4 D square, right? That is what the equation is. So if I take the area square, it will be pi by 4 whole square into D raised to 4. So instead of V square, I can substitute this equation into this equation. So substituting this is what I get. Okay, so the H, which is the difference of water level in the tank, will be equals to this equation, which is FL Q square divided by 2G into bracket pi by 4 whole square into D raised to 5. Now let us try to focus on every element. We already know what is H. Capital H is representing the difference of water level between the tank, and F is representing the frictional resistance that is offered. Okay, this is the frictional coefficient that is offered by the pipe material. L is representing the length of the pipe. Q is representing the discharge that is flowing in the pipe, which will remain constant. So it should be divided by, as you know, these are all coefficients, multiplied by d raised to 5 is there. So what is d? D is the diameter of the pipe. Okay, so if you know how much is diameter, if you know how much is discharge, length and frictional coefficient of the pipe, we could be able to calculate how much is the difference of water level that will exit. But if you want to know how much is the diameter of the pipe required to be connected between these two tanks, what we can do is we can send D to the other side and we can bring H to the right hand side, and by doing that we can again calculate how much is the diameter, right? So basically when you are designing a pipe, you know how much is the discharge that is required, you know how much is the length between the two tanks, and you may also know how much is the difference of water level that exists between the two tanks. So in that case you could be able to find out how much is the diameter by using this equation. Okay, so this is the equation which is used to calculate, or which is used to design a pipe. Okay, so let us solve this simple problem. I am going to read out this problem. There is a notes that I have given you in the classroom. So in the classroom, if you go and see, you will find this notes also. So I'm going to read this question and then we are going to solve the same problem over here. Okay, so the question is like this: the rate of flow through a pipe is 0.25 meter cube per second. The diameter of the pipe, which is 20 centimeter, is suddenly enlarged to 40 centimeter. The pressure intensity in the smaller pipe is 11.772 Newton per centimeter square. Determine the loss of head due to sudden enlargement, pressure intensity in the large pipe, power loss due to enlargement. So this is what the question is given to you. You can read a question one more time to understand what is given to you. So what I'll do is I'll write down all the given data first, then I'll write down all the things to be calculated. Okay, so the given data is such that rate of flow is given. Rate of flow is nothing but the discharge. So the discharge that is given to you is 0.25 meter cube per second. Then the pipe which is carrying it suddenly changes from 20 centimeter to 40 centimeter. It means what? There is a sudden enlargement in this case. So the sudden enlargement equation we need to use. So let us take the small d1 as 20 centimeter. So this is the pipe before the enlargement, and d2, which is diameter after the enlargement, which is the diameter of the larger pipe, is 40 centimeter. So d1 and d2 has been written. Now next one is the pressure intensity in the smaller pipe, which means before the enlargement, is 11.772 Newton per centimeter square, right? So what is to be calculated? We need to calculate how much is the head loss. So sorry, this is head loss due to enlargement. Okay, so we need to calculate this head loss. Then we need to calculate how much is the pressure intensity, and after that we need to calculate how much is the power lost due to this enlargement. Okay, so first let us calculate how much is the area. You can use your calculator and determine how much is the areas. So the area before the enlargement, we need to use 20 centimeter as diameter. So pi by 4 into 20 centimeter square will give you in terms of centimeter square. We can again further convert it in terms of meter square, because our discharge is in terms of meter square. We need to convert our area is also in terms of meter square. So you take this as 20 centimeter. If this is 20 centimeter, 0.2 will be your diameter in terms of meter. So substitute that and find out how much is area. So similarly, A1 and A2 will be calculated. So A1 represents the area with respect to 20 centimeter pipe, and A2 represents the area with respect to 40 centimeter pipe. So A1, A2 is calculated. Next we can calculate how much is V1 and V2. We know the continuity equation, Q is equals to A1 V1 is equals to A2 V2. So using that equation we can solve for V1 where Q is equals to V1 is equals to Q divided by A1, V2 is equals to Q divided by A2. We know how much is Q and we have determined A1 and A2. By solving this we will get V1 and V2. So V1 is 7.96 meter per second, V2 is 1.99 meter per second. So once you calculate this, the next step would be to solve the first thing, which is our head loss due to sudden enlargement. So we know the equation of head loss due to sudden enlargement, which is V1 minus V2 whole square divided by 2G. So substitute the V1, V2 in that equation and determine how much is head loss. So head loss is in terms of 1.816 meter. So after determining that, the next step would be to apply the Bernoulli's equation. So this is the Bernoulli's equation we have. He has not explained what kind of pipe it is, whether it is inclined or whether it is horizontal or anything. So let us assume that it is horizontal pipe. If it is horizontal pipe, Z1 will be equal to Z2. It means the elevation at the first pipe and the elevation in the second pipe will remain same. So Z1 is Z2 will get cancelled. So we already know how much is P1 by W, right? So P1 is given to you. So we have to convert this in terms of Newton per meter square and divide by 9810, which will give you what is P1 by W. So V1 square by 2G, V1 is there, we can calculate how much is V1 square by 2G, V2 square by 2G, which we have determined, and HL is also being determined. So first we will apply the Bernoulli's equation. Total energy at section 1 will be equal to total energy at section 2 plus of head loss, right? So where Z1 and Z2 are same, that will get cancelled out. So P2 will be equal to P1 by W plus of V1 square by 2G minus V2 square by 2G minus of head loss. So substitute what is P1 by W, then V1 square by 2G, then V2 square by 2G, and then head loss. So solve it, you will get to know how much is the power, how much is the pressure at the section 2 where the diameter is greater, okay, which is 12.96 into 10 raised to 4 Newton per meter square. Okay, so once you have solved this, the next step would be to solve the power lost. So if you want to solve for power equation, it will be WQ into H. Okay, now we are calculating how much is the power lost. So to calculate the power lost, we need to use how much is the head loss that has been taken place. So when water moves from a smaller diameter pipe to the larger diameter pipe, because of that sudden enlargement, the head that is lost is 1.816 meter. So henceforth we will use this in this equation. So W is the unit weight of water multiplied by discharge, which you already know, and substitute the value of head that has been lost in this equation and divide by 1000. So by dividing it 1000, we will get in terms of kilowatts. Okay, so if you only take WQ into H, it will give in terms of watts. By dividing 1000, we will get in terms of kilowatt. Substitute W, what is unit weight of water, 9810, what is discharge, 0.25, how much is the head loss, 1.816, divide by 1000. So we will get to know how much is power lost. So power loss due to sudden enlargement is 4.453 kilowatts. So what we will do is, we will solve more problems on this. You try to solve the problems that are given you in the notes. If you find any difficulty, you can ask me. Okay, thank you.